Hello everyone, and a very warm welcome to our deep dive into one of the most important ideas in all of electricity, alternating voltage. You might hear this term, also known as AC voltage, and think it's something complicated and only for engineers. But the truth is, you use it every single day. The power that comes from the electrical outlets in your wall, the power that charges your phone, runs your computer, and lights up your home, that is all thanks to alternating voltage. In this video, we're going to take this seemingly complex topic and make it simple. We'll use the diagram you see on screen to patiently walk through every single part. By the end, you won't just know the definitions, you'll truly understand how it all works together. So, let's begin. First things first, what does the word alternating even mean in this context? The best way to understand alternating is to compare it to its opposite, direct voltage, or DC voltage, which is what you get from a battery. A battery provides a constant, steady stream of voltage that flows in only one direction, from the positive terminal to the negative. It's like a river flowing steadily downhill. Alternating voltage, on the other hand, is completely different. It doesn't stay at a constant value, and it doesn't flow in just one direction. Instead, its value is constantly changing, and it periodically reverses its direction. A great analogy is the tide at the ocean. The water level rises smoothly, reaches a high point, then smoothly falls, passes its starting point, reaches a low point, and then rises again to repeat the entire cycle. Alternating voltage behaves in exactly this same cyclical, back-and-forth manner. Now, let's look at the heart of our diagram, the mathematical formula that perfectly describes this behavior, V of t equals Vm sine omega t. I know, seeing a formula can be intimidating, but think of it as a recipe. It's a precise set of instructions that tells us exactly what the voltage is doing at any moment in time. Let's break down each ingredient of this recipe, one by one. Let's start with the left side, V, T. The lowercase v stands for voltage. The letter T inside the parentheses stands for time. So, V, T, is pronounced V of t, and it means the voltage at a specific time, t. This is called the instantaneous voltage. Imagine you're watching a movie of the voltage changing. The entire movie is the alternating voltage cycle. The instantaneous voltage, V, T, is like pausing the movie at one exact frame and asking, what is the voltage right at this precise moment? Because the voltage is always in motion, its value at 1 second will be different from its value at 2 seconds. This V, T, is the part of the formula that gives us that specific, snapshot value. Now let's move to the first term on the right side, Vm. This is pronounced V sub m or simply Vm. The V again stands for voltage, and the M stands for maximum. So, Vm is the maximum voltage. This is the absolute peak value, the highest point that the voltage ever reaches during its cycle. On our graph, you can see the wave rises up to a crest. The height of that crest, from the center line up to the very top, is Vm. This value is also known as the amplitude of the wave. The amplitude tells you the intensity or strength of the voltage. A higher Vm means a more powerful voltage. For example, the wave also goes down to a minimum point. That minimum value would be negative Vm. So the voltage swings between positive Vm and negative Vm, but its peak magnitude is always Vm. This value is measured in volts. Next in our recipe is the sine function, written as sin. This comes from trigonometry, but all you need to know is that the sine function produces a very specific, beautiful shape, a smooth, repeating wave. It's this sine function that gives alternating voltage its characteristic wavy, cyclical pattern. It's what ensures the voltage rises and falls smoothly, not abruptly. Without the sine function, it wouldn't be the clean, predictable wave that we see on the graph. Inside the sine function, we have two more terms multiplied together. The first one is the curvy W symbol. This is the Greek letter omega. Omega represents the angular frequency. This might sound complicated, but the idea is simple. It's a measure of how fast the voltage is cycling. Imagine a dot on the edge of a spinning bicycle wheel. Angular frequency is like telling someone how fast the wheel is spinning. It's not measured in miles per hour, but in an angle measurement called radians per second. What's a radian? It's just another way to measure an angle, like degrees. A full circle is 360 degrees, which is equal to exactly 2 times pi radians. So, omega tells us how many radians the cycle sweeps through every second. A larger omega means the wheel is spinning faster, and therefore the voltage is completing its back and forth cycles more quickly. And the final piece of our formula is the lowercase t, which, as we mentioned before, simply stands for time, measured in seconds. This is our variable. As time moves forward, the value of t increases, which in turn causes the whole omega t part to increase, and the sine function uses this changing value to create the rising and falling voltage wave. So, let's put it all together and look at our graph. The vertical axis represents the instantaneous voltage, V, t. The horizontal axis represents the progression of the cycle, omega t. The wave starts at 0. As time moves on, it rises smoothly until it reaches its highest point, the maximum voltage, Vm. This occurs when the cycle is a quarter of the way through. Then, it curves back down, passing through 0 voltage when the cycle is halfway complete. It continues its journey into the negative region, meaning the current is now flowing in the opposite direction, until it hits its lowest point, negative Vm. Finally, it rises back to 0, completing one full, perfect cycle. The amount of time it takes to complete one of these full cycles is incredibly important. It's called the time period, and it's represented by a capital letter T. You can see it marked on our graph, spanning the full length of one wave. Now, let's look at the formulas on the right side of our diagram. These are practical tools that connect all these concepts. First, we see a crucial relationship, omega equals 2 pi f. We already know omega is the angular frequency. The new letter here is f, which stands for frequency. Frequency is measured in a unit called Hertz HC. Frequency is perhaps a more intuitive way to think about how fast the cycle is. It simply tells you how many complete cycles occur every single second. For instance, in North America, the standard frequency is 60 Hz. This means the voltage in your wall outlet goes through 60 full back and forth cycles every second. That's so fast, our eyes can't see it, which is why a light bulb looks like it's shining steadily. In Europe and many other places, the standard is 50 Hz. This formula, omega equals 2 pi f, beautifully connects the two ways of measuring speed. Since one full cycle is 2 pi radians, it makes perfect sense that if you have f cycles per second, your total speed in radians per second, which is omega, would be f times 2 pi. From this, we can easily get the next formula by rearranging it, f equals omega divided by 2 pi. This just shows that if you know the angular frequency, you can easily calculate the standard frequency in Hertz. And finally, we have the last, simple relationship, t equals 1 divided by f. T is the time period, and f is the frequency. This relationship is beautifully logical. If frequency f is the number of cycles you complete in 1 second, then t, the time it takes to complete just one of those cycles, must be 1 second divided by that number. Let's use our 60 Hz example. If the frequency is 60 cycles per second, then the time period for one cycle is t equals 1 divided by 60, which is about 0.0167 seconds. An incredibly short amount of time for one full cycle. And there you have it. From a single formula, we have unpacked an entire world of concepts that describe the electricity we use every day. To recap, alternating voltage is a voltage that changes its value and direction in a smooth, repeating cycle. This cycle is perfectly described by the sine wave equation. Vm is its peak value or amplitude. Omega and f describe how fast it cycles, and t describes how long one cycle takes. All these concepts are interconnected and give us a complete picture of alternating voltage. I sincerely hope this detailed explanation has made this topic clear and accessible for you. Thank you for watching. If you found this guide helpful, please consider liking the video and subscribing for more in-depth tutorials. If any questions remain, please ask them in the comments section below. We'll see you next time.